Thank you very much for the introduction, and thank you for the invitation. As we were just saying, I'm very sad that we can't be there, or that I can't be there. Some of you are there. Mostly I'm sad that I can't hear your talks because of the time difference, and I'm actually really sad that I can't get beers with all of you after the talks. But still, this is a really great event, and I'm excited to talk about harmonic analysis techniques for almost minimizers. All of this is joint work with some subsets of Guy David, Mariana, Smit, Vega, Garcia, and Tatiana, Toro. Some of this is old stuff, so I apologize if you've seen it before, but I'll talk a little bit about new, not even yet on the presses work at the end of the talk. Cool. So let me give you a talk preview. It's already late in Europe, so if you need to fall asleep for the talk, at least you'll get a vague idea of what it's about. So the study of elliptic PDE in rough domains, which you've probably heard a lot of talks about, has been helped by tools and ideas from variational calculus, from free boundary problems in particular. And today we're going to try to give back. We're going to try to help the study of variational problems using tools and ideas from harmonic analysis and GMT. And so what's the basic idea? We'll study these things called almost minimizers, which have a variational characterization. They minimize up to some error, but they don't necessarily satisfy a PDE. And that's why we need to use these techniques from harmonic analysis and GMT, as opposed to sort of the classic techniques that grew out of the Georgi-Nash-Moser school. And the reason why harmonic analysis and GMT is so good in this situation is that these minimization properties lead to scale invariant and quantitative regularity. And as harmonic analysts and GMT people, this is what we're really good at, proving these types of results. So yeah, some older results, some newer results, and please feel free to interrupt me whenever you have a question. I would love that. If we can keep this interactive, especially since it's late in the day, that sounds great to me. Cool. Okay, so let me get into it. You've probably seen this a bunch, but some people are just tuning in or have missed some of the talks because of the time difference. So I'll sort of go over some of this a little bit quickly. We have this measure, which is called hitting measure or harmonic measure. You can think of it probabilistically as running a Brownian motion and asking when it's going to leave your domain or where it's going to leave your domain. Of course, you can also think of it from the Riesz representation theorem and the maximal principle. If f is a continuous function and omega is a nice enough domain, there should be a unique harmonic extension of the boundary values of f into the interior of omega. And this unique harmonic extension, if you evaluate it at every point, gives you a linear bounded functional. And so there should be an associated measure to every point, which we call the harmonic measure. Cool. And this is the standard picture that everyone steals from Matthew Badger about harmonic measure. Cool. So I want to understand how harmonic measure talks to sigma, which is the surface measure supported on the boundary of the domain. So either my domain is smooth or sigma is the n-1 dimensional Hausdorff measure restricted to the boundary. And I don't really care so much about the pole right now, so don't worry about that too much. So what do we want? We want quantitative well-posedness, right? We want that small changes in the LP norm of f means small changes in U of f. And by linearity in the maximal principle, if p is infinity, or if f is a continuous function, really, this is true. But if p is between 1 and infinity, it requires some work on our part, right? And it's sort of harmonic analysis 101 that you get quantitative well-posedness exactly when you have that u of f is equal to f in the sense of some suitable limit. Here it's a non-tangential limit, right? So our domain looks like this. We draw a sort of interior cone. And then if you approach through this interior cone, u of f should be equal to f, right? And, you know, these are sort of standard techniques that we know that if you have some sort of quantitative bounds, then limits work out really nicely. Cool. And it turns out, and this is also sort of standard or folklore at this point, that if omega is a nice domain, and don't worry too much about what nice means, you get this quantitative well-posedness exactly when the harmonic measure is mutually absolutely continuous in a scale invariant and quantitative way with surface measure, or when it's an A infinity weight. And this makes sense, you know, if you know a little bit about this subject, there are some non-tangential maximal functions involved. Maximal functions are LP bounded with a weight when the weight is an A infinity weight, right? So all of this sort of makes sense in terms of I don't know, the harmonic analysis you learned from Stein's book or something like that. Cool. So what's the big question? Well, what conditions on the domain imply that the harmonic measure is an A infinity weight, right? When do we have quantitative well-posedness? There's a ton of work here. So if I attempt to cite any of it, I'm going to offend like 80% of the audience. And there's lots of other really interesting directions that have popped up recently and not so recently: perturbative theory, other types of elliptic PDE, higher codimension. I'm going to skirt all of that to avoid doing a good job or a bad job. There's two works that I want to highlight, though. One is work of David and Jerison from '90 in the Indiana University Math Journal. And it says that if omega is quantitatively open and connected, is an NTA domain, for those of you who know, and the boundary of omega is quantitatively n-1 dimensional, alpha is regular, again, for those of you who are familiar, then indeed we have this quantitative well-posedness, we have this A infinity weight condition, which is great. And then another highlight is a little bit more recent work of Jonas, Steve, Chema, Mihalis, and Chalvi, which was published recently in Invenciones, gave sharp characterizations of the domains in which the Dirichlet problem is quantitatively well posed. And this is beautiful work that was the culmination of a century plus of really intense harmonic analysis. And that's pretty much all I'm going to say about it, because we're actually going to go in the other direction. So let me do a little bit more review. And I'm sort of speeding through things, so hopefully I'll slow down. Perhaps you remember that for every domain, which is nice enough, there's something called a Green's function. So the Green function has a pole at x is in omega, and this Green's function is positive inside the domain. It's 0 on the boundary, and it's harmonic. Well, it's not quite harmonic, right? Its distributional Laplacian, that's a typo, is a Dirac delta mass at x, okay? So this is, something that sort of exists through some functional analysis mumbo jumbo, if you'd like, but you really need very few conditions on the domain in order to have this item exist. But what's important about this item is that if you do a little bit of integration by parts, and if everything is smooth and you work formally, then the normal derivative of G on the boundary, this nu is meant to indicate the unit normal, is exactly the Rada-Nikodym derivative between the harmonic measure and the surface measure. So again, I'm assuming everything is smooth, all the measures are mutually absolutely continuous, all of that kind of stuff, right? So in some sense, if I tell you a domain and I tell you what I want the harmonic measure of that domain to be, I'm really doing a boundary value problem for the Green's function, where I'm specifying both the Dirichlet and the Neumann data, right? I'm saying, here's my partial omega. There's some mysterious function u, which is harmonic. I'm telling you exactly what I want d nu to be here. And I'm telling you that u equals 0 here. And you can't specify both Dirichlet and Neumann data. It's an overdetermined problem. But that means that if you know something about the harmonic measure of the domain, you have a chance about knowing something about the domain itself, right? So in particular, we can ask this question without immediately thinking that we're going to fail. If we know something about this Rada-Nikodym derivative, does that mean that we know something about the boundary? So the easiest example of this is the following fact, which is kind of nice. If omega of x is equal to a constant times surface measure, and if omega is bounded, open, then x is equal to, or maybe, all right, then omega is equal to b x r for some r bigger than 0. So omega is a ball, right? And your pole is at the origin. So there's some sort of nice rigidity here in the 0th order case where harmonic measure is proportional to surface measure. Cool. So this is stuff that I think probably you've seen a lot, or that maybe you're already familiar with, either in this conference or from research. So, I'll stop if you have any questions, but then I'll move on to things that are a little bit different. Okay, let me move on to things that are a little bit different that you've maybe seen less of. So I'm switching gears completely. I'm going to introduce this functional, which was first introduced or first studied rigorously by Alt and Caffarelli in 81, and then Alt-Caffarelli and Friedman in 86. These two functions here, you can think of them as being smooth or like Holder continuous. And these characteristic functions, right? This is just 1 when U is positive and 0 otherwise, 1 when U is negative and 0 otherwise. And we're integrating all of this. Okay, this functional was first introduced to study jet cavitation, which I guess is what happens when you get like pockets of air inside of rushing water. Seems kind of cool. But what's important to notice is that you can differentiate this functional. It's a little bit difficult. This is not Calculus of Variations 101 because the functional is not continuous. These characteristic functions here kind of screw everything up for you. But still, if you're clever, you can differentiate it. And you get the following set of Euler-Lagrange equations. U is harmonic whenever U is not equal to 0. And then there's two scenarios. If you're at a point where both the positive and the negative phase touches, then d nu from the positive side of U squared minus d nu from the negative side of U squared, oh wait, I don't want these squares, sorry, is equal to Q plus squared minus Q minus squared at this point, Q. And if you're at a point where only one phase is present, then d nu plus or minus of U is exactly equal to Q plus or minus. So if you'd like, you're taking some domain. Let's ignore Q minus just for a second. You're taking some domain. And if this domain is the positivity set of a critical point to this functional, then you should think that U kind of looks like the Green's function. And thus, the harmonic measure, the Radon-Nikodym derivative of the harmonic measure, should be pretty much equal to Q. So there's a relationship between critical points of this functional and exactly the domains which have prescribed harmonic measure that we care about. Cool. So unsurprisingly, given the close relationship between these problems, the ideas of Alt-Caffarelli and Alt-Caffarelli-Friedman have been used a ton in harmonic measure problems. In the one-phase work of Carlos and Tatiana, where they show that the oscillation of the Poisson kernel controls the oscillation of the unit normal, just because some caloric measure stuff has come up a little bit, and because, I don't know, shameless self-promotion. In the parabolic setting, the time-dependent setting, these ideas have also been adapted in my thesis to show that the oscillation of the parabolic Poisson kernel controls the regularity of the boundary. This very beautiful paper that I talked about before uses an object called the Alt-Caffarelli monotonicity formula, Alt-Caffarelli-Friedman monotonicity formula, to show quantitative connectedness. This is a really beautiful application of this idea. And in fact, this Alt-Caffarelli monotonicity formula has found usage in a lot of harmonic measure problems, especially in two phases. I think Marti talked about the Alt-Caffarelli-Friedman monotonicity formula a little bit earlier. We've seen this very nice paper quoted earlier. The first place I know of where they use this monotonicity formula to study a two-phase free boundary problem for harmonic measure is in this beautiful paper of Carlos, David, and Tatiana. And more recently, in the resolution of Carlson's epsilon squared conjecture, a modified version of the Alt-Caffarelli-Friedman monotonicity formula was used. So this area of free boundary problems has given us, as members of this conference, a lot. But we don't want to be only takers and not givers, right? You want to be a mensch, you want to give back. And so that's sort of the purpose of this talk. But before I dive into that, I'll take another drink of water so you can ask me questions if you have them. So it's time to give back. But before we can give back, we need to introduce a couple definitions. So we say that U minimizes our functional if for every ball inside of our domain and every function which is equal to U outside of that ball, the energy of U is less than the energy of V, right? So what's the schema? Here's our domain. Here's our ball. Outside here, U equals V. Inside, U and V can differ. But if U is a minimizer, then the energy of U should be smaller than the energy of V. We're going to consider what are called almost minimizers, right? So if you put your hand over this part of the definition, it's exactly the definition of minimizers. But instead, we have this error. And this error, we want to be uniform, but we want it to get small in the radius of the ball. Okay, and what is this n plus alpha? Well, some preliminary calculations can show you that if you take this integral in a ball of radius x, grad u squared plus q plus characteristic function of u greater than 0 plus q minus characteristic function of u less than 0, that this should be roughly on the order of r to the n. So this term here is getting smaller faster than the main energy restricted to the balls that you care about. So you should think of it as being a higher order term, maybe something like noise, right? This can represent like a noisy measurement in your model, for example. So a really natural example of how almost minimizers show up all the time is when you try to minimize an energy where you add terms that are of lower order. So I think I have a little bit of time. Maybe it's worthwhile for me to do this computation for you. So something you can note is, let's say you take a ball centered at a point where u equals 0 and of radius r. This term inside of the ball of radius r is going to be approximately of size r to the n. But this term inside of the ball of radius r, well, if u grows proportional to its distance from the boundary, then u is going to look something like r inside of this ball of radius r, because we're centered at a point where u equals 0. And so this term should look something like r to the n plus 2. And so indeed, if you minimize this functional, you get an almost minimizer to your original functional. You have to do a little bit more work to look at balls that are centered far away from the free boundary and balls that are centered close to the free boundary, but not on the free boundary. But I'm not going to show you the whole proof. It's a fairly straightforward approach to these things. Cool. Yeah. So this is a sort of standard example of where these almost minimizers show up. So let me tell you a little bit about why you might care about almost minimizers. We've already seen that they show up when you have lower order terms in the functional, or they represent some sort of error in measurement. They show up a lot when you do constrained minimization. So if you're trying to find a domain on a, let's say, Riemannian manifold with area 5, but where lambda 1, the first tertiary eigenvalue, is as small as possible, it turns out that this domain will be an almost minimizer to the Alt-Caffarelli functional. And this shows up a lot in quantitative stability, especially quantitative stability problems for eigenvalues. And there's some philosophical reasons why you might care about almost minimizers. They don't satisfy an equation, or they can satisfy an equation, but one which is different than the equations that come from the critical points of Alt-Caffarelli. So it's not going to be necessarily true that every almost minimizer satisfies a PDE. On the previous page, when we looked at j tilde, which was equal to j plus this extra term, u squared, the PDE is now going to be something like Laplacian u plus u equals 0 when u is not positive, right? So the nature of the Euler-Lagrange equations can change when you look at almost minimizers. This allows us to focus on what we can just figure out purely from the variational characteristic and ignore these pesky equations, right? So I'm saying that, people like DeGiorgi, Nash, and Moser, they led us astray in the 20th century. Obviously, I'm joking, but they put too much PDE inside of the calculus of variations. And if you want to go back to the variations, you can deal with almost minimizers. This is particularly useful for problems where the Euler-Lagrange equations are messy in some way, and so you don't want to rely on them as much. Non-local free boundary problems, for example. And let's note that the functional is not convex. It has this weird characteristic of the positivity set terminate. So you shouldn't expect that every critical point to the functional is in fact a minimizer of the functional. And it's true, there are some critical points which are not minimizers. There are functionals that satisfy the Euler-Lagrange equation, but which don't satisfy the minimization property. Cool. So hopefully this motivates studying almost minimizers sufficiently. Okay, so now we want to study almost minimizers, and the first thing to do is to understand the regularity of the functions themselves. So I made a really terrible error. Let me go back a little bit so I can tell you a little bit more about what's going on here. So remember, when you look at minimizers of this functional, Laplacian u equals 0. So I'm working over here. And here is the free boundary of where u is positive. If you know that this free boundary here is nice and smooth, then you know that the function itself is also going to be really smooth, right? Because you have this function that satisfies Neumann conditions or Dirichlet conditions on this very nice and smooth free boundary. So in some sense, understanding minimizers of this problem is a question of understanding what the free boundary looks like. So I just sort of wanted to make that point right there. So going back, before we can understand the free boundary, we have to understand the regularity of the function itself. And so these papers of Alt-Caffarelli and Alt-Caffarelli-Friedman tell us that minimizers of these functional are Lipschitz, they're non-degenerate, they're smooth inside of their positivity set, and they have nice compactness properties under their limits. And then, more recently, Guy David and Tatiana Toro first studied almost minimizers of these functionals, and they showed that the exact same thing was true for almost minimizers of the functionals. And then even more recently, joint with Mariana, Smit, Vega, Garcia, and Guy and Tatiana, we showed that this regularity of the function itself also holds for minimizers with variable coefficients. So this is important when we're talking about the problem I was talking about before, understanding, for example, optimal domains for eigenfunctions on Riemannian manifolds, where this matrix A will then come from the Laplace-Beltrami operator. And we always assume some sort of Holder regularity or non-degeneracy or something like that. The key idea in all of this is that almost minimizers have nice compactness properties. So generally, limits of almost minimizers are almost minimizers, and pseudo blowups of almost minimizers are minimizers. So let me try to explain that a little bit right now. Imagine you have an almost minimizer U. It's an almost minimizer in this domain. And then what you want to do is understand the behavior of U in small balls around this point X. So you do what perhaps people now understand is pretty standard. Let's call this point X0. You take a rescaling where you turn this ball into the unit ball of size 1 by saying U of X0R is equal to Rx plus X0 over R. And then it turns out that U of X0R is a C R to the n plus alpha, almost minimizer. Maybe I should make this an R0, 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 R0. So on the previous slide, right, we defined these C alpha almost minimizers. Here's your C, here's your alpha. And what I'm telling you here is that as you zoom in, the C is getting smaller and smaller and smaller. So in particular, when you take a limit, when you let R go down to 0, what you'll get in the limit is actually a minimizer of the Alt-Caffarelli functional or Alt-Caffarelli-Friedmann functional, not just an almost minimizer. And this fact that the infinitesimal behaviors of almost minimizers are in fact minimizers is hugely important and comes out of the work that I talked about on the previous page. This first idea that the general limits of almost minimizers or almost minimizers is sort of a quantitative thing. So I guess what I'm trying to say is, imagine you had UI, which were all C alpha almost minimizers, and you did something to prevent them from getting infinitely large. Maybe you asked that like the energy of all the UIs is inside of some omega is bounded by some M. Well, then you might assume that the UI is passing to some subsequence converges some U0, which is also a C alpha almost minimizer. And so you should expect to be able to get some sort of quantitative information out of this compactness, right? This feels very GMT-y to me, at least. Cool. So I told you that regularity of the free boundary is the most important thing. So let's talk about the regularity of the free boundary. This paper of Alt and Caffarelli for the one-phase problem. So here you should think of Q minus as being identically equal to 0. And let's assume that Q plus has some Holder regularity. We also want Q plus to have some non-degeneracy. So Q plus stays away from 0. Then it turns out that minimizers satisfy what's called a flat implies smooth result. So if your free boundary is Reifenberg flat, it's contained in the neighborhood of a plane, then in a smaller ball, the free boundary is in fact smooth. And what this means is that the free boundary has two components, a regular part and a singular part. The regular part is open. It's locally given by smooth graphs, so C1 beta functions. And the singular part is small. It's got Hausdorff measure less than, let's say, n-3. There's actually a lot more results, even cutting edge results on how small the singular set is, what kind of structure it has, but those aren't so important for the topic we're going to have, or the topic of today's talk. In work that's now, I guess, a couple years old, God, what year is it? With Guy David and Tatiana Toro, we proved that the same theorem holds for almost minimizers to the one-phase problem, right? So where Q minus equals 0. And a key step in proving this Holder regularity was actually a theorem that maybe feels a little bit more familiar or a little bit more in place for this conference, which is that if you take a minimizer to this problem up here, now there's no assumptions on Q plus and Q minus besides maybe non-degeneracy and let's say they're L infinity. Then the positive and negative sets are quantitatively open and quantitatively connected, NTA domains. And the boundary of the positive and negative sets are AHLFORS regular domains. They're quantitatively n-1 dimensional. So in particular, the positive and negative sets are chord arc domains and have uniform rectifiable boundaries. If those terms don't mean anything to you, don't worry about it. All we're saying is that we have some quantitative scale invariant regularity here for almost minimizers. Oh, this should be almost minimizer. And I want to point out that this second theorem that I've written due to myself, Guy, and Tatiana is not a curiosity. It's actually a key point in the proof of the Holder regularity for this first theorem. So we need to use these ideas from geometric measure theory and harmonic analysis in order to prove this problem. And Alt and Caffarelli didn't even mention any of these words like AHLFORS regular and NTA domains. This is purely a PDE proof, uses the maximum principle like all Caffarelli proofs in an incredibly clever way. Cool. So I think I have about 15 minutes. My hope is that for 10 of those 15 minutes, I'll sketch some aspects of the proof of this theorem here And then for the last 5 minutes, I'll tell you a little bit about the stuff that will hopefully come out in the next month or so. Great. Take a sip of water, give you a chance to absorb. Cool. Okay. So let's start with quantitatively open. The idea here is that the quantitative openness uses the fact that, again, this should be almost, that almost minimizers U are Lipschitz and non-degenerate. So how does it use this fact? Well, what does non-degenerate mean? Non-degenerate, it means for all, or maybe I should say, there exists a C greater than 0, such that for all Q in the boundary of the positivity set, and for all R bigger than 0, there exists a point which I'll provocatively call AR Q, A plus or minus, and this is a point in plus or minus U greater than 0, such that these points are not very far from Q, and such that U at these points, A plus or minus R of Q, is bigger than C times R. So it's saying that U grows linearly off the free boundary. So you have some point on the free boundary here, Q, and there's some point, A plus or minus R of Q. And at this point, U is not very small. But because U is Lipschitz, that actually means that in a ball containing this point, U is not very small, which tells you that in a ball containing this point, you're still in the positive or negative set. And this is what gives what people call corkscrews, which is the quantitatively open characterization. Oh, so here I was supposed to highlight not quantitatively open, but quantitatively connected. And this follows from the fact that global minimizers to J are locally connected. So what do I mean by that? I mean that you're never in a situation, maybe I should say, the positive and negative sets of global minimizers to J are locally connected. So you're never in a situation where in a small ball, you have something like U greater than 0 here, U greater than 0 here, but then U equal to 0 here. This doesn't happen. And that kind of makes sense, right? It doesn't feel very energetically favorable to do all the hard work of getting all the way down to 0 and then getting all the way back up to positive. You probably just should have stayed positive the whole way through. So this is a cool fact about global minimizers. It actually follows from this Alt-Caffarelli-Friedman monotonicity that I talked about before. And then to show that you have quantitative connectedness, what is called Harnack chains, you use a compactness argument and this fact about global minimizers in the limit to prove what you want. So what am I trying to say? Quantitatively connected means that if I have 2 points here, both in the positivity set, I can draw a chain of balls between them, and the chain of balls is not too long, and these balls don't get too close to the set where U equals 0. And if you contradict that, right, then you'll get a sequence of almost minimizers, which will converge to a globally defined minimizer, which has non-locally connected positive or negative sets. This is what gives you the Harnack change. So I don't know. Hopefully these sort of schematics of the proofs are somewhat interesting and not just completely mad ramblings. And then the final proof I want to talk about is the AHLFORS regularity. So let's just remember, here's, let's say, the boundary of where U is positive. And what I want to show is that Hn minus 1 of any ball centered on this boundary, let's call this gamma, is roughly r to the n minus 1. But it turns out that it suffices to show that there exists a measure mu such that mu of bxr intersect gamma is roughly r to the n minus 1. You don't necessarily need it to be surface measure in order to show this AHLFORS regularity. And so what is this measure going to be? Well, inside this ball centered at x of radius r, I'm going to define a competitor, hxr. hxr is going to be equal to my function u outside of the ball, and then is going to be the harmonic extension on the inside of the ball. And now we use properties of harmonic functions on NTA domains, things that come from the work of Jerison and Koenig, for example, in their paper, which has been cited several times today, to produce this measure mu, which is exactly going to be given by d mu d sigma is equal to the normal derivative of hxr. So it's basically going to be the harmonic measure of the domain. So I'm just trying to give you a sense of how some of these tools from harmonic analysis and GMT come into play here. Cool. Okay. So all the results I've been talking about in terms of regularity of the free boundary have been about one-phase problems where Q minus is equal to 0. But I introduced the problem as being a two-phase problem, right? Having a weight on the positive side and a weight on the negative side. The reason why I haven't talked about two phases as much is because they're much harder. And the reason why is what are called cusp or branch points. So here's a nice schemata. This figure is due to Guido, Luca, and Bojo. And the idea is that in a two-phase problem, you could have some points on the free boundary where the two phases come together, and then some points on the free boundary when the two phases don't touch each other. And you understand what's going on here, where you have one phase points, and you understand what's going on here when you only have two phase points. But when the two types of free boundaries come together, something very complicated is happening. In particular, if you're centered at a point like this, at this scale, you could look like a two-phase point at a large scale, and then start looking like one-phase points when you zoom in. And this transition makes the analysis very difficult. So it turns out that we understood regularity for the one-phase problem for a long time. We understood regularity for points where both phases come together. This is work of Daniela da Silva and her collaborators from the mid-2000s. But only recently, like 2 or 3 years ago, did we figure out how to transition between these two types of regularity, between the two phase points and the one phase points. And this is due to a very nice paper of Guido di Filippis, Lucas Polaro, and Bojidar Velichkov in Invenciones 2021. There's a similar phenomenon, this analysis of branch points or cusp points, which occurs in minimal surfaces of higher codimensions and is similarly quite difficult to handle. And this analogy between minimal surfaces and the free boundary problems is an important one. So it's easy to construct examples of critical points and minimizers with no two phase points or with only two phase points. So let me draw some examples. If you're in some domain like this, it's not hard to find boundary values such that the minimizer looks like this, or such that the minimizer looks like this. but it's actually quite hard to construct boundary values such that the minimizer looks like this. It's hard to sort of make sure that that happens, essentially. And I mean, this is an important question, right? We spent all these decades trying to understand the regularity near these branch points, but if the branch points never exist, then we're sort of wasting our time, right? There was a very nice recent preprint of Guido, Luca, and Bojo, where they use quasi-conformal mappings to produce critical points, things that satisfy the Euler-Lagrange equations, whose free boundary contains these branch points. And they prove some structure theorems for these branch points, but this uses the theory of quasi-conformal mapping, so it's only good for n equals 2. And these are critical points, not necessarily minimizers. So in work in progress with Guy, Mariana, and Tatiana, we construct examples of minimizers to the two-phase function, where the two weights are the same, q plus and q minus are both identically equal to 1, which can exhibit branch points in 2 and 3 dimensions. And these are truly minimizers. So we construct some domain, which is a long, thin box, and we basically show that the free boundary needs to sort of look like a pair of ellipse. So here u is positive, here u is negative, here u is 0, and the free boundary will, this is a terrible drawing, will come together at these branch points, right? So this is a minimizer to j of u, which is right u squared dx plus the volume of where u is bigger than 0 plus the volume of where u is smaller than 0. And the key tool we use to show the existence of these branch points is Dahlberg's theorem for the absolute continuity of harmonic measure with respect to surface measure in Lipschitz domains. So we thought that was kind of cool, that we could like use harmonic analysis and GMT techniques again to prove this type of existence. A big open problem about these branch points, which I encourage you to think about, and I'm happy to talk to anyone about, is the structure of these branch points. The study of minimal surfaces suggests the following conjecture, that if you're a minimizer to the two-phase functional, then the set of branch points to your free boundary should be contained in an n-2 dimensional C1 manifold. So maybe your free boundary looks like this. Right here, u is positive, u is negative, u equals 0. And since I'm drawing all of this when n equals 2, what I'm asking is that this be a 0-dimensional set with isolated points, right? And that's what it looks like here. But a priori, the branch points could accumulate. So when n equals 2, for critical points, this aforementioned preprint of Guido, Luca, and Bojo confirms this conjecture using quasi-conformal mappings. And the conjecture is still wide open when n is bigger than or equal to 3. I think it's a really interesting and important problem. Let me just end my talk by saying that we prove in this upcoming work that an analogous conjecture for almost minimizers is 100% false. So pick any closed subset of Rn minus 1, the Cantor set, if you'd like. We can construct an almost minimizer with, let's say, q plus and minus both identically equal to 1, such that the branch points of the free boundary of this almost minimizer are exactly the Cantor set, right? So you have your Cantor dust here, and basically the almost minimizer free boundary has branch points at exactly this Cantor set. And let me just say that here, the key idea are the regularized distance functions, which come up in the higher codimension work of Guy David and Joseph Fenoy and Svetlana Maybaroda, and other collaborators, many of whom are in the audience. So again, it's kind of fun that we have this idea from harmonic analysis, which is helping us out with these variational problems. Anyway, that's all my time. I hope you enjoyed the talk. Thank you very much for the attention, and please enjoy the conference.